Is my slides visible to everyone?
Yes, sir.
Yes, sir.
Okay.
Yes, sir.
So as you all are aware that this course is CLL 251 heat transfer, and we are going to look at the conduction today. So that's why I have written conduction here. I am Dr. Manoj Kumar Amteke, and the book which we are going to follow is BK Datta. So this book you can buy from Amazon, or if you wanted to get a soft copy from anywhere, I don't mind, but get this book. Okay. This book will cost you around 300 or 400 rupees, not more than that. Okay. So before we look at the course strategy, I just wanted to ask you uh, what information you have gathered about this course from your friends. Talk to your friends about this course. Any of you? Any input? Have you
Uh,
discussed anything about this course with your seniors? Maybe some other.
that this course is very important in terms of internship opportunities because it most of the questions are asked from the heat transfer part.
Okay. Uh, that's good. Other than that, anything about how this course is conducted every year? Uh, Good, bad, easy, difficult?
Sir, I spoke to two seniors and they said that it was one of their preferred courses, like some one of their more fond courses in this semester. So it left a good impression, right, sir?
So one of the easier course, that is what they said.
No, nothing about easy difficult, but that they liked the course a lot. So they felt like they enjoyed it. That's it.
Okay. So this year, particularly in this semester, this course is going to be little bit difficult. Why it is going to be difficult, I will explain. Okay, just a minute. So can you see the slides? Is it visible? The slide is visible to
Yes, sir.
Yes,
everyone?
sir.
Okay. Uh, so this is a 4 credit course. Again, what course strategy which we are going to follow is we will have one minor examination which is in general scheduled by Dean Academic Office, and other than minor one, we will have 2 quizzes. Okay, so total we will have 3 examinations. These 2 quizzes we ourselves will schedule at some time in between. Okay, again these 2 quizzes will be scheduled in a class time, so that you will not have any overlap, and all 3 examinations will have 30 marks each. Okay, the strategy which we are going to follow is out of these 3 examinations I am going to count base 2. I'm going to count base 2 out of these 3 examinations. But if you miss, let's say, more than 2 examinations, there will not be any makeup examination. No re-quiz or re-minor if you miss more than 2 exams. So you have a choice of missing one. But if you miss more than one, there is no re-quiz, there is no re-minor. Is it clear to everyone? Again, so only 2 examinations I'm going to count, so that becomes a total of 60 marks. So remaining 40 marks we will have a major examination at the end. Okay. The next point is all examinations and quizzes will be conducted online on Moodle. Okay, so all exams and quizzes will be conducted online on Moodle, not on MS Teams. These will be conducted on Moodle. The one thing which you all have to remember here is many of you are thinking that this is just an online semester, so examinations will be easy. The difficult part comes here. So difficult part here is all the examinations will be proctored. This is a very important thing. All examinations will be proctored. How this will be proctored? I am going to divide all 200 students into different groups, around 20 groups in 20 students in each group, and each of these groups will be monitored by TAs or me or some faculties. Okay. And these teams will be made in MS Team. So even though you are solving your examination on a Moodle, but you will be online on MS Team on each of these individual, MS Teams. If any of you switch off your video, we will consider you as a upset. If any of you is found doing unfair means, his case will be immediately reported. Okay. So examinations will be conducted with utmost seriousness and with utmost sanctity. Okay, no cheating. I generally I hate cheaters, so no cheating will be allowed. Whatever things are required to curb that, we will do that. Okay. Other than that, classes and tutorials will be conducted online on MS Teams, as we are doing the class today on MS Team. Grading will be relative and audit pass grade will be 30 marks and above. Okay, so is it clear? Course strategy is clear to everyone?
Yes, sir.
Yes, sir.
Another thing which I wanted to tell you is all the lectures will be recorded on MS Teams, but tutorials will not be recorded. Tutorials, you all have to attend the tutorials every day and do your calculation. Okay, again, I'm recording the lectures on MS Team. Every lecture will be recorded, but that is going to be there as long as a reasonable number of students are attending the classes. If I see the attendance of the class is decreasing, then classes will also not be recorded. Okay, I want the students to attend the class. I want them to go through the material. And if the students are not attending the classes, I will stop recording. So only those who are attending the class regularly, they will get to know. Is it clear? I wanted to be as lenient as possible, provided that you also try to help me, isn't it? I am trying to put a lot of hard work, but in return I want you also to put a hard work. And if I see at some point of the time that only I am doing the hard work and students are not ready to put their share, then that relaxation is gone. Okay, it is two-way process, isn't it? See, it's not that only I am teaching you, you also teach me something, isn't it? Correct. Many of things I also get from the students. So it's a two-way process. It's not a one-way process. And I don't like when it becomes a one-way process when students are not attending the classes. So if I see students are not attending the classes, then no classes will be recorded. It will be done online. Whoever attend the class, he will get to know. Clear? Is it clear to everyone?
Yes, sir.
Okay. Another point which I wanted to say is all the examinations will be conducted on Moodle and questions will be made new. No questions from previous year will be repeated. Most of the time I don't repeat my questions, but none of the questions will be repeated whatever has been done previously, not at all. So I want each one of you to attend the class. I want each one of you to go through the material and pass this course fairly. Okay. Okay, so let's move to the next part. The syllabus of this course is going to be, we will start from conduction. So we will have steady state, unsteady state conduction. Then we will look at the heat transfer coefficient, which is important when we are looking at the convection. Then we start looking at the forced convection and free convection. Thereafter, nucleation and boiling, which is important in chemical engineering applications. Finally, radiation. And at the end, we are going to look at the design of different heat exchangers and evaporators. So this is the syllabus. All these topics are individual chapters in this book, BK Datta. Okay, heat transfer by BK Datta. Again, heat transfer is a widely studied subject. I have seen that the students are copying correlation from some other books and then they claim that my correlation is correct or your correlation is correct. Nothing doing. We are saying that the heat transfer book by BK Datta is going to be followed in this particular course. So the correlation should be taken from this book, not by searching it on a Google and taking some XYZ correlation which is available on Google. Okay. Otherwise, if I will provide the correlation in the question paper itself. So don't come to me later on claiming that the correlation which I have used is correct. I have searched on Google and this is also correct. Nothing doing. We will not accept that. That is why we are making it clear in the starting itself that we are going to follow this book BK Datta. Heat transfer is a widely studied subject. You will get at least 100 correlation on one topic, isn't it? All these correlations are correct, but then I have to grade the examinations, isn't it? Correct. So you might claim that your answer is correct based on whatever the different correlation which you have used, but considering the entire examination process, we wanted to have some unique answers, isn't it? Otherwise, that uncertainty is there. So in order to avoid that uncertainty, we will follow the correlations or the equations given in this book or otherwise given in the slide. Okay. If the correlations are given in the slide or in the reading material or in the question paper, whatever the equations I have provided, if you are using that, it's perfectly all right. Is it clear to everyone? Hello?
Yes.
Hello. Okay. So again, one more thing is all lectures will be recorded on MS Teams, but the recording remains only for 20 days. So it is your job to download it. Okay. As long as we are recording it, you will have to download it. If you don't download it after within this period of 20 days, then don't send me email saying that I have not downloaded, please provide me. It's not possible. Okay. So it is your responsibility to download it in a given time. All right. So is there any question so far? I'm sorry to starting this class with difficult and yes, please go ahead. Hello. Any questions so far? No question. See, even today, how many students are attending? See, it's just 120 students are attending. This course has almost 200 students. Okay, that means the remaining 220 students are there in this course. That means remaining 100 students are thinking that they will get it everything freely. Okay, and this is what I don't like. Get the point, isn't it? So you all are working hard. I am working hard, but some students feel that they should get it, easily. Do you think that all the remaining 100 students do not have their internet working? We are not fool, isn't it? 5-10 people should be there, isn't it? Maybe even 20-30, but not 100. Correct. So please do this course seriously, and I am going to be very serious in this course. If I see things are not moving in a correct way, I will stop sharing the recorded videos. I will do everything online. If some malpractices are going on, I'm going to report it. I have not done it so far, but I'm going to do it this time. Okay. I'm going to do it because unless somebody pulls the string, nobody understands. Isn't it? So other than that, let's enjoy the course. Let's enjoy the course. You ask as many questions as possible, so that it becomes interactive, isn't it? Okay. All right. All right. So let's start with the course. So as I said that, heat transfer is a widely studied subject. The reason for that is it is extremely important, not only in chemical engineering, but also across the disciplines. Okay. So heating or cooling of material is an indispensable part of processing, production, fabrication, shop floor jobs in engineering practice. That's why I am putting it in a generalized way. It is not only important in chemical engineering, but across the branches. Okay. Again, why to study heat transfer? Studying of heat transfer is extremely important because we wanted to minimize the loss or gain of heat during the process, because unless we do that, we will not be able to operate the process in a most economic way. So if you are heating the process, heating some equipment or cooling some equipment, definitely the cost is incurred in that, isn't it? And any process we wanted to perform, that has to be performed in a most economical way in order to make profit. Okay, so that is why studying the heat transfer is one of the widely is the most important subject, and it is most widely used across the branches. Okay, so let's look at one simple example of chemical engineering process. So this flow sheet is for nitric acid production. So nitric acid is produced from ammonia. So ammonia reacts with oxygen in the air in presence of catalyst platinum, that gives NO2, and this NO2 then further reacts with water to produce the nitric acid. Okay, so this is what the reaction scheme is. So here you can see the water is present at the room temperature, but ammonia is in general stored at -33 in a liquid state. That means for storing the ammonia, you continuously need to provide the refrigeration, isn't it? Isn't it? So you have to reduce the temperature of this ammonia container throughout in order to maintain the ammonia in a liquid state at -33 degrees Celsius. Okay, so this ammonia, which is actually at the -33 degrees Celsius, is first vaporized in the vaporizer, and this vapor of ammonia is then mixed with the compressed air. So air is compressed using this multi-stage compressor, and this compressed air and the vaporized ammonia is mixed and charged to the reactor. In the reactor, the temperature is around 800 degrees Celsius. So we are starting from -33. Now the temperature is 800 degrees Celsius. So this reaction mixture, which is comprised of NO2 at 800 degrees Celsius, exchanges heat with the waste heat boiler, and the temperature of this outlet stream decreases to 275 degrees Celsius. So heat is recovered here using the waste heat boiler. Still, the temperature of the outlet stream is around 275. So this heat is further recovered in the downstream equipments like tail gas preheater and economizer before the temperature of this reaction mixture comes out to be room temperature, and then this reaction mixture is then charged to the adsorption tower where it reacts with the water. This adsorption process is also exothermic. So you can see that we are starting from -33, then we are moving to 800, then it decreased to 275, then it is further decreased to room temperature. So here not only the refrigeration effect is required, but also heating of the reactor is required, and thereafter this heat of the reaction mixture has to be recovered by different units, isn't it? Unless we recover this heat, this process will not be economical, isn't it? Correct. So even a simple process of converting ammonia to nitric acid requires refrigeration, heating, recovery of the heat. All sort of complications are involved in this process. So you can see that how important this particular subject is when we are talking about the chemical engineering or process applications. Is it clear to everyone? Hello?
Yes, sir.
Okay, so this is the reason why the heat transfer, is one of the most important subject in chemical engineering. Okay, I give another examples of the other engineering aspects. So the first example is a power plant. If you look at in the power plant, you can have high rating boilers which exchanges heat heat from the hot combustion gases and the white hot refractory furnace wall to the water boiling inside the array of tubes. So this is very important. Why important? Because here the heat transfer is also accompanied with phase change, isn't it? So water which is in the liquid state in these tubes then converted to steam. Okay. Also, all three modes of heat transfer are taking place here. So there is a heat transfer from the furnace walls to outside, which is primarily through conduction. There is a heat transfer from this white hot refractory furnace to this array of the tubes, which is primarily because of radiation, and also this combustion gases are moving in the chamber. So there the heat transfer is primarily by the convection. So all three modes of heat transfer are taking place here, isn't it? Finally, the steam coming out from the turbine has to be condensed in a huge surface condensers. So there is a boiling as well as condensing. Both are there. Okay. Another example is for a rolling mill of an integrated steel plant, where the large metal blocks are shaped into sheets, which are then cooled by flow of water. Okay. If we consider the example of nuclear plant, in a nuclear plant, further complicated things are there, because depending on what type of nuclear plant you are having, the heat transfer or the heat is taken by sometimes by the liquid metals. Okay. So some more complications are there in the nuclear plant, nuclear power plant. Okay. So with these examples, now let's look at why heat transfer is important in engineering application. So heat transfer is the transport of heat energy from one point in a medium to another in the presence of temperature gradient or a temperature difference. Both are important here. Sometimes the temperature difference at 2 points may be same, but still there could be a temperature gradient if the medium is having the heat generation. So you will not have a horizontal line for the temperature distribution, but instead you will have a parabolic curve. So even though two end points are at the same temperature, but in between you will have a temperature gradient. That's why both these words are used here. Okay, so heat transfer takes place if there is a temperature gradient or temperature difference. Driving force for the heat transfer is the temperature difference between 2 points in the same medium, or the 2 points between two mediums which are in a thermal contact. Again, heat transfer involves the detailed study of physical mechanism of transport of the heat energy in various practical situations. Why I am saying various practical situations? Because sometimes you will see the heat, the flow across the solid surfaces. Sometimes you will see flow through the pipe. Sometimes you will see the flow through different heat transfer equipments like shell and tube heat exchanger, or a plate and frame type of heat exchanger, spiral type of heat exchanger. So various practical situations are there. In this practical situation, how the transport of heat is taking place, that has to be studied in a detailed manner. Okay. Again, with this study, we also wanted to size or design these equipments for a better heat transfer. Okay, so how many number of tubes should be used? What should be the size of shell? How many plates should be used in a plate and frame heat exchanger? All this sizing and design is also studied in this course, which is heat transfer. Is it clear to everyone what I'm trying to say?
Yes, sir.
Stop me if something is not clear in between. Okay. Again, if you look at heat transfer and thermodynamics, seems very close to each other, but there is some minute difference between these two. So heat transfer talks about the kinetics. It talks about the speed or the rate of heat transport. Okay. Whereas thermodynamics gives only the extent, whether this heat transfer is possible or not. Isn't it? If we disturb the equilibrium, how much maximum heat transfer can be there? This extent is given by the thermodynamics. But what will be the rate of this heat transfer, that we calculate in a heat transfer course. Okay, so there is a minute difference between heat transfer and thermodynamics. Thermodynamics only gives the possibility whether there is a heat transfer possible or not, and the maximum extent. Heat transfer gives what will be the rate of heat transfer. Okay, is it clear to everyone?
Yes,
Yes,
sir.
sir.
So again, I'm repeating the same thing which you might have done in your, JE days, but just for a sake of continuity, I will still, give some discussion on these modes of heat transfer. Probably you all have done it in a much more detailed way earlier. Okay. So there are three modes of heat transfer: conduction, convection, and radiation, out of which conduction and convection are most commonly present modes. However, the radiation heat transfer is important when there is a higher temperatures are present. So other than that, if the temperatures are around room temperature 50 degrees Celsius, around 100 degrees Celsius, we ignore this radiative heat transfer in such cases, even though radiation is present in all temperature above the absolute zero. All right. So conduction heat transfer is an atomic or molecular process. Conduction is a atomic or a molecular process. It occurs in the presence of temperature difference and is not accompanied by any macroscopic or a bulk motion of the medium. So what we are trying to say here is it's an atomic and a molecular process, and in conduction we don't see the movement of the fluid element from one point in the medium to the another point. So there is no macroscopic or a bulk motion of the medium. Okay. Conduction is the only mode of heat transfer in a solid medium. It may also occur in a stagnant liquid or gaseous medium, but often in liquid and gaseous, the more prominently present mode is a convection. But still, the conduction can occur for liquid and gaseous medium. Conduction is again similar to the diffusion and governed by a Fourier's law of heat conduction. So we will see this Fourier's law of heat conduction as we progress. So a typical schematic is shown here. Here you can see the left hand side face of the slab has the temperature of 25 degrees Celsius. Right hand side surface is having 500 degrees Celsius. So there will be a heat transfer taking place from this 500 degree Celsius surface to this 25 degrees Celsius surface. Okay, so I have again shown by a different color here just to appreciate. So unlike the conduction, in convection, the transport of heat is primarily because of the displacement of fluid element. So fluid elements are moved from one point to another point at a different temperature in a medium. Okay. Again, the convection has two types: forced convection and free convection. And as the name suggests, forced convection occurs whenever the displacement of the fluid element primarily caused by an external mechanical unit such as pump or agitator, pump, blower or agitator. So if you are mechanically creating the turbulence in the medium, and because of that heat is getting transferred by the displacement of fluid element from one point to the another, then this is called as a forced convection. Unlike this, in a natural convection, the movement of the fluid element from one point in the medium to another point with a different temperature primarily occurs because of the adverse density gradient. So as you can see here that if the temperature at the bottom here is higher, around 500 degrees Celsius, and at the top it is 25, so fluid elements, those are present at the bottom, will become lighter and they will move at the top because of buoyancy. And this type of movement of the fluid element and the corresponding heat transfer is referred as natural convection. So convection is quantified primarily using the Newton's law of cooling. So Newton's law of cooling gives the heat flux is directly proportional to the temperature difference. Is it clear to everyone?
Yes, sir.
Conduction is governed by Fourier's law of heat conduction, whereas the convection is governed by Newton's law of cooling. Correct? Is it clear?
Sir, could you please repeat the free convection ones?
Okay. So free and natural convection occurs when there is a motion of the fluid medium is caused by adverse density gradient. Adverse density gradient. So that you can see here in this particular schematic figure at the bottom. Here you can see the temperature at the bottom surface is 500 degrees Celsius, whereas the temperature at the top surface is 25 degrees Celsius. So what will happen to the fluid elements which are present at the bottom? Because of higher temperature, their density is going to be lower, isn't it? Correct. And because of that, these fluid elements which are present at the bottom will move up because of buoyancy force, isn't it? So movement of the fluid element here is primarily because of adverse density gradient. I am not using any mechanical pump or blower or agitator here for the movement of the fluid element. It is occurring naturally by the density gradient, isn't it? So when the heat transfer is caused by such movement, which is primarily because of adverse density gradient, then the heat transfer is called as a natural or a free convection. Is it clear now?
Sir?
Yes.
Yes, please go ahead.
Sir, what exactly does adverse density gradient mean? I mean, what does that
So see,
adverse?
okay, if I put the temperature of 500 degrees Celsius at the top and 25 degrees Celsius at the bottom, what will happen? Still there is a density difference, but the fluid element will not move from top to bottom. Get the point?
Yes,
Still
sir.
not clear?
Got it.
Okay, so that's why see this movement of the fluid element takes place for a specific case only if these fluid elements are at the bottom, isn't it? The lighter fluid elements are at the bottom. If the
Yes.
lighter fluid elements are at the top, there will not be any movement. So that's why this word adverse is used. All right. Can we move? Yes, please go ahead.
Sir, you said the convection is governed by Newton's law of cooling. Sir, can you explain what is the basis of Newton's law of cooling?
Okay, so we will get back to that. But see, unlike the convection, convection, if you look at convection, primarily looks at the macroscopic flow of energy. Okay, even though we are looking at the macroscopic flow of energy at the molecular level, it is governed by conduction. But this effect of conduction and the velocity which is present in the convection, that everything is coupled in the another coefficient which is called as a heat transfer coefficient. So that heat transfer coefficient, if you account, you will see that the heat flux is proportional directly to the temperature difference, unlike the Fourier's law of heat conduction. Okay, so we will get back to the more details of these later. In fact, we will derive this entire thing. Okay, but just to give you a perspective, why the heat transfer is governed by a different equation here is because it also accounts the velocity effect, unlike the conduction where there is no velocity effect. Here remember, there is a velocity effect because the fluid is moving from one point in the medium to the another point. But in conduction, there is no macroscopic or a bulk motion, so there is no velocity. Is it clear? Still the perspective is not clear?
Sir, it is clear. It is clear.
Okay, so we will derive this equation in detail later, but we get a different equation primarily because we also count a bulk motion. Okay, bulk movement, unlike the conduction where we don't account the bulk motion at all. Okay, all right. Okay, so the last mode of heat transfer is a radiation, and as I said that the radiation can take place at any temperature about above the absolute zero temperature. So a body at a temperature above absolute zero always emits energy in the form of electromagnetic waves. Again, the rate of release of such energy is proportional to the fourth power of the absolute temperature. So this is what called as a Stefan-Boltzmann law. Again, this particular law also we will derive from first principle. But for a time being, consider that this is true. So in a Stefan-Boltzmann law, you will see that the emissive power is proportional to the fourth power of the absolute temperature. Okay, sorry. So this mode becomes significant at a higher temperature. Again, all bodies are not equally good emitters of radiation. So a standard or a perfect emitter called as a black body is used, and so this is just a standard. Black body is nothing but a standard, and all the bodies are compared with respect to that, and the property which is used for this comparison is nothing but the emissivity. Okay, so the black body will have the emissivity equals to 1, but then you can have a different body like a gray body, you can have the diffused gray body, etc., which will have a lower emissivity. Another quantity which comes into the play is nothing but a view factor. So whenever we are calculating the radiative heat transfer, not only the emissivity is important, but also a view factor. So what is view factor? View factor is basically a fraction of the area of a body which can be seen by another body. So for instance, how much heat will be transferred from this particular body to this another body is also depend on how much area of this body B is seen by a body A. That is called as a view factor. So we will look at these details, these concepts in more detail later on. Is it clear to everyone? All right.
Yes, sir.
Okay. So let us start with the conduction. So far we were only having a brief discussion on different modes of the heat transfer, but we will start with the conduction today, and then eventually we will move to convection and radiation later on. So let's look at the steady state conduction in one dimension. We will move to multiple dimensions as well as in unsteady state as we move ahead. So conduction of heat, as I said, means of transport of heat energy in a medium from region at a higher temperature to a region at a lower temperature without any macroscopic motion in the medium. That's what we have said, isn't it? In conduction, there is no bulk motion of the medium. Again, in the solids, the conduction primarily takes place because of vibration of the molecules at their equilibrium position. Okay. In metals, the heat conduction occurs primarily due to drift of electrons than by molecular vibration. So molecular vibration takes place in a crystalline surface, crystalline solids. Whereas in metal, primarily the heat conduction takes place by the drift of electrons. So electrons are moving from one point in the medium to the another point in the medium, and therefore this movement of the electron is also similar to the movement of the gas particles, and therefore these are also referred as an electron gas. Since the heat transfer or a heat conduction in a solid primarily in metals takes place by the drift of electron, the materials having good electrical conductivity is also possesses good thermal conductivity. Okay, so because both are taking place because of the drift of electron. In gaseous medium, the heat conduction takes place because of the collision of the molecules. Collision of high thermal energy molecules with low thermal energy molecules, so they transfer their kinetic energy with the collision. Similar phenomena is partially responsible for the heat conduction in solid, but as I said, in liquid, as I said, in liquid primarily the heat transfer takes place by a convection. But if the stagnant liquid is there, in such cases the heat transfer is primarily by conduction. So even though convection we are considering as a separate mode of heat transferred. But if you look at microscopically, convection is not a true mode of heat conduction, true mode of heat transfer. In fact, convection is also primarily because of conduction at microscopic level, at a microscopic level. Okay. Is it clear to everyone, or is it confusing?
Sir, could you repeat that, please?
We are considering convection as a separate mode of heat transfer. Okay. Macroscopically, that is okay. But if you look at microscopically, the convection is because of conduction itself. Convection we are considering separately because we are also including the effect of velocity and everything in that, and that we are looking at a macroscopic level. But in a microscopic level, the heat transfer primarily takes place by a conduction itself, because of the movement of the electron, because of the vibration of the molecules. At the microscopic level, these are the modes of heat transfer. Even the fluid elements are moving macroscopically from one place to the another, but if you look at microscopically, primarily this heat transfer is taking place because of the vibration or the movement of the electron itself. That's why we are saying that convection, even though we are considering it as a separate mode of heat transfer, but actually if you look at a molecular level, it is primarily because of conduction itself. Is it clear now, everyone?
Sir, I have a question.
Please go ahead.
Sir, if it is a conduction at a lower level, then why Fourier law of heat conduction is not valid for fluids as well? In convection case.
Very good question. So now if you apply the Fourier's law of heat conduction for each of these molecules, will you able to solve your heat transfer problem for the fluid mixture which is present in your reactor? Now we have to solve this Fourier's law of heat conduction for all the molecules present. Can you do that? You get the point? Still not clear?
Sir, but if we consider the behavior of any one particle and integrate, like that integration is one of the options now to do that. So why can't we do that?
That's what I'm saying. So see, if you try to apply the conduction equation at molecular level, then you will have, large number of equations to solve. Okay. And in addition to that, you will also have to look at the velocity effect in between, because these molecules are also some effect of this movement of the particle will also be there, isn't it? So therefore, solving the heat transfer problem becomes difficult. In fact, this Newton's law of cooling, if you look at its derivation, if you look at that, primarily comes from the conduction. We start with the conduction, but then we say that solving this conduction problem is difficult. Solving this conduction problem is difficult because we are not only looking at the heat transfer problem, but also we are looking at the velocity problem. I give another example. Navier-Stokes equation you all might have seen, isn't it? But the exact solution of the Navier-Stokes equation nobody has solved so far. In fact, that is one of the seven millennium problem. Correct. We solve the Navier-Stokes equation only in a approximate form. Either we assume that inviscid flow, either we assume that it's a Stokes flow, and then some of the terms are eliminated, and then we solve. The problem which you people are asking, in that case, you have to solve that Navier-Stokes equation in addition to the Fourier's law of heat conduction, both. And that becomes difficult, and therefore a more approximate equation is used, which is in terms of Newton's law of cooling. Okay, get the point? But molecular level, at molecular level, the heat transfer primarily takes place by conduction, even though macroscopic level it is because of convection, because convection includes velocity effect, everything in an abstract way. Is it clear? Still not clear?
Yes, sir, it's clear.
So as we will progress,
Sir, can I ask one question?
please go ahead.
Sir, in our previous course, CLL 110 transport phenomena, sir said that Fourier's law of heat conduction is analogous to Newton's law of viscosity. Like
Newton's law of viscosity, yes.
Like this, Q is the rate, heat rate,
Yes,
rate of heat transfer.
I'm not saying Newton's law of viscosity here. I am saying Newton's law of cooling.
No, sir. I know the difference. I was just asking that it is analogous because the Fourier's law of heat conduction, the equation Q is equal to A Ka upon T1 minus T2 upon T. So if we take A here, Q upon A, then it becomes heat flux. Q upon A, because Q is the rate of heat transfer, and if rate upon area is heat flux. So heat flux is equal to K T1 minus T2 upon T. So it becomes like heat flux is equal to a gradient of temperature upon time. It is analogous to that Newton's law of viscosity.
Yes. I'm not denying.
Momentum flux is equal to Newton's law of viscosity coefficient upon that velocity gradient upon that. So I was just asking that means this like conduction was the transfer of, here the conduction is transfer of heat. So in that case, in transport phenomena, I'm just trying to clear that point. The momentum flux was also the momentum flux was also getting transferred. The momentum was also getting transferred in that fluid.
Yes. So see, in convection, both these, momentum transfer as well as heat transfer, both problems are coupled in convection. Both problems are coupled because velocity also comes into the picture there if you are looking at the convection. But in conduction, there is no momentum transfer. There's only a heat transfer. That's why only Fourier's law is applicable there. But when we are looking at convection, both momentum transfer as well as heat transfer, both are important. That's why I'm saying that in addition to solve the Fourier's law of heat conduction, you also need to solve the Navier-Stokes equation. That's what I say.
Okay, sir. Okay, sir.
In convection, I'm saying in convection, not in conduction. In conduction, only Fourier's law of heat conduction is sufficient. Make sense? Is it clear or not clear?
Yes.
Okay. All these things you will get to know a little bit in more detail as we progress. Okay. We are going to solve some complicated situations as we progress. But right now we are only, barely starting on the concepts. Okay. All right. So as I said that Fourier's law. Okay. So let's look at the Fourier's law of heat conduction. So it states that if two plane parallel surfaces each other having a area A are separated by a distance L and are maintained at temperature T1 and T2 respectively, such that T1 is greater than T2, the rate of heat conduction Q at a steady state through the wall is given by this. Q is given as Ka T1 minus T2 by L. Here Q is nothing but the heat transfer, and the unit of that is given as watt, which is nothing but joule per second. K is the thermal conductivity. Again, the unit is watt per meter per degree Celsius or watt per meter per degree Kelvin. L is nothing but the width of this wall, that is given in meter, and T1, T2 can be given in Kelvin as well as degree Celsius. Doesn't matter because we are taking the difference of the temperature here. Okay. So as one of the student is already said, the same Fourier's law of heat conduction can be represented in a differential form like this, where Q small qx is nothing but the heat flux. Heat flux is nothing but the heat conduction per unit area normal to the x direction. So qx is given as minus k dt by dx, and this equation is similar to the Newton's law of viscosity. Okay, it is also similar to the Fick's law of diffusion. That's why we are saying that conduction is similar to the diffusion. Okay. So here qx is given as minus k dt by dx, where dt by dx is nothing but the temperature gradient in a x direction. So the temperature, again here the minus sign is there because the heat is getting transferred from higher to the lower temperature. So that's why this minus sign is coming in. Is it clear to everyone? This you might have already done in transport phenomena, this part, right?
Yes.
Can we move ahead? Is it clear to everyone? Hello, am I audible?
Yes, sir.
Yes, sir. Yes.
Oh,
Yes,
okay,
sir,
all
yes.
right. All right, thank you. So now, as I said, this is a very important thing. Okay. Now in this particular equation, Qs is the heat flux, dt by dx is nothing but the temperature gradient. But the property which we wanted to look at in more detail is K, which is nothing but thermal conductivity. So thermal conductivity, similar to viscosity or diffusivity, uh, is a fundamental property. Is a fundamental property. Okay. This is a fundamental property of material which basically gives the measure of effectivity of material to transfer the heat through it. Okay. Again, this thermal conductivity depends not only on the chemical constitution, but it also depends on characteristics of material. So whether the material is solid, liquid or gas. Also, it depends on the nature of the solid state. So whether the solid is crystalline or amorphous. It also depends on the physical conditions like temperature, pressure, etc. Okay, so these are the different aspects uh, uh, which which affect the thermal conductivity. If you look at the crystalline material in general have a high thermal conductivity than amorphous material, because this crystal structure enables vibration, and therefore the heat is getting transferred easily. Remember I said that the heat transfer, the conductive heat transfer takes place because of the vibration of the crystals, isn't it? So crystalline material enables that easily, and therefore the crystalline material will have a higher thermal conductivity than the amorphous material. Thermal conductivity of metals generally decreases with the increase in temperature. Generally decreases with increase in temperature, except for aluminium. Again, the thermal conductivity of metals decreases with impurity. And pure metal has the highest thermal conductivity. Again, the solid substances having low thermal conductivity. Okay, so some solid substances which has the low thermal conductivity, these are called as insulators. And these insulators are very important in heat transfer, because very often we wanted to reduce the heat transfer from the process equipment. For instance, if you are transferring the steam through a pipe, we don't want it to release that heat to the environment, and therefore all these steam pipes are applied with the cladding, isn't it? So there is an insulator applied around this steam pipe. Okay, so these insulating material are extremely important in the heat transfer, isn't it? So the solid substances which are having the low thermal conductivity are called as insulators. Very often these are having the high void fraction. So why I am saying that, uh, I don't know how many of you have opened the fridge in your room, in your home. Have you opened the fridge in your home? Backside of the fridge? Backside of the fridge I'm saying, not the front side. Have you ever opened the and seen how the backside of the fridge is? Okay, so have you seen some foam type of material there?
Yeah, sir.
So that is a polyurethane foam. That is nothing but a polyurethane foam. So why foam? Why not just a slab of polyurethane is used? That is the question. Anybody?
Sir, maybe because the foam contains air and air is a bad conductor.
Yes. As I said that, as we move from solid, liquid and gas, there is a order of magnitude change in the thermal conductivity. Solid will have thermal conductivity in, hundreds, 500, 600, in that range. Liquid water has the thermal conductivity in the range of 1 or something. And the gases will have 0.01 or something, isn't it? So there is an order of magnitude difference in the thermal conductivity. So if you are including the air in that, see, this foam will have the air embedded in between, isn't it? And because of that, even though the thermal conductivity of the polyurethane foam is, it still is lower, because of polymers are not a good conductor, but because of this air trapped in between, it further decreases. So overall thermal conductivity of this foam further decreases. Okay. So high void volume fraction makes the insulator more effective. That is what we are trying to say here. The presence of gas is more responsible for insulating property than the thermal conductivity of the material. But the thermal conductivity of the insulating material increases with temperature. Why I am saying increases with temperature? Because the thermal conductivity of the gases increases with temperature. And since this foam comprises of air in large fractions, since the thermal conductivity of the air is increasing, therefore the thermal conductivity of this entire foam also increases with temperature. There are other insulators are also there like clay, bricks, zirconia, alumina, etc. All right, is it clear to everyone?
Sir, why do crystalline materials have more thermal conductivity?
So crystalline material will have the crystal structures, and these crystal structures will remember the heat is transferred because of the vibration of the crystals, isn't it? But if we, let's say, have the amorphous material, there will not be a vibration. That's why crystalline material is more thermal conductivity than the amorphous material.
So they don't have any vibrations, molecules?
No, they will have some, but not as high as crystalline material.
Oh, okay.
Okay. Okay, so let's move to the next point. Next point is the thermal conductivity of liquid generally decreases with temperature. So this is same as you might have seen viscosity also decreases with temperature, isn't it? So there is some molecular theory is there behind all these observations. So we are not going through that. That probably you can look at in some more standard references. Okay. So, but one more exception is there. This exception is water and glycerin over a certain temperature. So this water is a very peculiar. Even water is abundantly available. Everybody thinks that we, see the water every day, but this is one of the most peculiar molecule. Okay. Again, except for liquid metals, water has the highest thermal conductivity. So liquid metals will have in general more thermal conductivity, and that is why liquid metals are used in nuclear reactors for transferring heat. Commonly used the liquid metal is sodium. Sodium is used in this remember these fast breeder reactors are there. So fast breeder reactor which is there in Kalpak, it is there in Kalpakam, isn't it? If I'm not wrong. So there they use this sodium for transferring the heat. Okay. Sodium is used for transferring the heat. All right. Thermal conductivity of the gases increases with the temperature and decreases with the molecular weight, and therefore hydrogen will have the higher thermal conductivity, whereas the high molecular weight gases like radon, etc., will have a lower thermal conductivity. All right. As I said that the thermal conductivity, the order of magnitude is different when we are looking at solid, liquid, and gases. So solid will have the highest thermal conductivity. Lower than solid, we will have a liquid, and then even lower than liquid, the thermal conductivity of the gases will be less than even liquid. So typical values are for silver, thermal conductivity is around 410 watt per meter Kelvin. For water, thermal conductivity is 0.63 watt per meter Kelvin. And for air, it is around 0.0262 watt per meter Kelvin. Remember these values, at least order of magnitude. Very often this type of question people ask in the interview. Okay, what is the order of magnitude for the thermal conductivity for metals, water, or air? Okay. All right. Again, very often we take thermal conductivity as a constant average value, but in some cases you will find that the thermal conductivity is a linear or a quadratic function of temperature. It's a weak function of temperature. Okay, so K is given as K naught 1 plus AT plus BT square, where A and B are some constants, and K naught is the thermal conductivity at 0 Kelvin, absolute 0. Again, when thermal conductivity is varying with direction, in that case, the material is referred as anisotropic. All right. Is it clear to everyone?
Yes, sir.
Okay, so let's look at the steady state conduction through a composite wall. So let's have, a composite wall made up of three type of material: material 1, material 2, and material 3. Material 1 has the thermal conductivity of K1, material 2 has the thermal conductivity of K2, material 3 has the thermal conductivity of K3. Again, the thickness of material 1 is L1, thickness of material 2 is L2, and thickness of material 3 is L3. And the cross sectional area of all three material is same as A. So in this case, since the cross sectional area is same, the rate of heat flow at steady state through individual layer is equal. So typically we equate small q, which is nothing but the flux. But what is flux? Heat flux is given as nothing but what? Rate of heat transfer per unit area. And since area is constant in this case, we are also equating capital Q. So capital Q1, which is nothing but the heat transfer through the slab 1, capital Q2, which is nothing but the heat transfer through slab 2, and capital Q3 is heat transfer through the slab 3. All three are same as Q because their cross sectional area is same. If their cross sectional area would have been different, in that case we would have equated small q1 same as small q2 same as small q3, isn't it? But in this case, since the cross sectional area is same, we are equating capital Q. Is it clear to everyone? Is it clear to everyone?
Yes, sir.
Again, this resistance and this electrical circuit, we will come back to this. What this is. Okay. The only point we wanted to appreciate here is the heat transfer resistances can also be arranged in a series. In this case, you can see that the heat transfer resistances are in series. So this can also be arranged in a series in a similar way that of electrical resistance. But we will prove this in the next slide. Okay.
Sir, can you repeat that point? When if the areas were not equal, then
small q
Q1
we should equate. In that case, the small q heat flux should be equated.
means heat flux at every contact would be same.
But since the cross sectional area, so heat flux is what? Heat transfer, rate of heat transfer divided by area, isn't it? And since area is same, we can equate capital Q in this case. All right.
Yes, sir. Yes, sir.
Okay. Okay. So let's look at this given example little bit in more detail. Again, for a simplicity, let us assume that the thermal conductivities of the layer are independent of the temperature. The temperature distribution in each layer, since this thermal conductivity is independent of the temperature, you will see that the temperature distribution in each layer will be a linear. So here you can see this temperature is linearly decreasing. Here it is linearly decreasing. But in individual slabs, we will have a different slopes. Why? Because the thermal conductivity of individual slabs are different. Okay, but the temperature distribution will be linear. But if this thermal conductivity is, let's say, dependent on the temperature, in that case, you will have a curved lines. You will not have a straight line. Is it clear to everyone? If thermal conductivity is dependent on the temperature, in that case, we will not get a linear decrease in the temperature in each of these slab. Instead of that, we will get a curved lines. All right. So here you can see that the temperature T1 is on the left hand side of this surface 1, and temperature T2 is on the right hand side of this surface 3, and T dash and T double dash are interfacial temperatures in between. So T dash is the interfacial temperature between 1 and 2, whereas T double dash is the interfacial temperature between 2 and 3. So let's apply the Fourier law of heat conduction here. So let's apply the Fourier law of heat conduction for layer 1. If we apply, remember the Fourier law of heat conduction is given by what? Q is given by thermal conductivity into area multiplied by temperature difference, isn't it? So temperature difference in this case will be what? Since we are assuming that T1 is greater than T2, so heat is transferred through transferred from T1 to T2. So here in this case, the temperature difference for the first lab will be T1 minus T dash and divided by L1. So the same equation we can derive from this. So I'm using the same equation here, this same equation. K into K1 will be the thermal conductivity of slab 1. Area is same. T1 minus T1 minus T dash, isn't it? Divided by M. This we can derive directly from this flux equation as well. It's not difficult, isn't it? So K1A T1 minus T dash divided by L1, that will be given by Q, because we are assuming that the heat transfer through all these three layers is same as Q, isn't it? We can rearrange this equation. So after rearranging this equation, the temperature difference T1 minus T dash is given as Q into L1 divided by K1A. Similarly, for layer 2, we can write Q is given as Q, or Q2 is given as K2A T dash minus T double dash divided by the thickness of this second layer, which is nothing but L2. We can rearrange this and we can get the temperature difference as T2 dash T dash minus T double dash, and that is given as Q into L2 divided by K2A. Similarly, for layer 3, we can write this equation as Q3 is given as Q3 or Q is given as K3A T double dash minus T2 divided by L3. And we can rearrange this equation as T double dash minus T2 is given as Q into L3 divided by K3A. Now, all these temperature differences we can add. If we add these temperature differences, this T dash get cancelled out with this T dash, this T double dash get cancelled out with this another T double dash, and finally what we get is T1 minus T2. So T1 minus T2 overall temperature difference is given as, this Q is common, so I can take this Q as common, L1 by K1A plus L2 by K2A plus L3 by K3A. We can rearrange the equation like this, and if we rearrange this equation further, what we get is Q is given as T1 minus T2 divided by L1 by K1A plus L2 by K2A plus L3 by K3A. So here you can see the numerator is what? Numerator is nothing but the overall temperature difference. T1 minus T2 is the overall temperature difference, whereas the denominator is what? Denominator is nothing but the overall resistance. Overall resistance. So L1 by K1A is the individual resistance for layer 1. L2 by K2A is nothing but the individual resistance for layer 2. And L3 by K3A is nothing but the resistance for layer 3. So here you can see this equation, we can write this equation as rate of heat transfer is given as temperature driving force divided by thermal resistance. And this is analogous to the equation which we use in the electrical engineering, isn't it? So current is given as potential difference by electrical resistance. So there is an analogy between the heat transfer and current. Okay, so thermal resistance in this case is R1 is given as L1 divided by K1A, R2 is given as L2 by K2A, and R3 is given as L3 by K3A, and all the resistances are in series, and therefore these are added to give the overall resistance. So overall resistance RT is given as R1 plus R2 plus R3, and that is nothing but this complete denominator, and that is given as T1 minus T2 by Q. So overall temperature difference divided by the rate of heat transfer, Q. Okay, so based on this, we can conclude that the thermal resistances are also additives if the resistances are in series, and therefore we have shown these thermal resistances in a similar way as that of the electrical connection. So here you can see the thermal resistances are added between T1 and T2. Is it clear to everyone?
Yes, sir.
All right. Okay. So now based on this, let's solve one problem and then we will stop today. So let's look at one example, one solved example here. Okay. So the example is the wall of the cold storage consists of 3 layers, an outer layer of ordinary brick, which is having a 25 centimeter thickness, a middle layer of cork, which is having the 10 centimeter thickness, and an inner layer of cement, which is having the thickness of 6 centimeter. The thermal conductivity of the materials are, for brick it is 0.7, for cork it is 0.043, and for cement it is 0.72 watt per meter degree Celsius. The temperature of the wall is 30 degrees Celsius and that of the inner layer is minus 50 degrees Celsius. Calculate the steady state rate of heat gain per unit area of the wall. So we wanted to find out Q by A, or if you are using the unit area, in that case we are interested in finding Q, capital Q. Okay. Again, we wanted to find out the temperature at the interfaces. So what are the temperature at the interfaces of brick and the cork layer? So we are interested in finding out T dash. Also, we are interested in finding out the temperature at another interface, which is between cork and the inner layer. So we are interested in finding out T double dash. And the temperature T1 is given as 30 degrees Celsius and T2 is given as minus 50 degrees Celsius. Also, we wanted to find out the percentage of the total heat transfer resistances offered by individual layers. So what is the percentage resistance offered by a brick layer, cork layer, and the cement layer? And finally, if the additional thickness, okay, so the last part of the question is, if you wanted to decrease the rate of heat transfer by 30%, then how much should be the increase in the thickness of the cork layer? That is what the question is. Is this question clear to everyone?
Yes, sir.
Yes, sir.
Okay. So let's calculate the individual resistances of each layer. So we calculate the resistance of brick layer. So brick layer resistance will be given by L1 by K1A. Again, we are assuming that the unit area, assume area equals to 1 meter square. So it is given as L1 by K1. So K1 value we already know. K1 value is 0.7 and the thickness L1 is also given 25 centimeter thick. So this is given as 0.25 divided by 0.7. So that comes out to be 0.357 degrees Celsius per watt. Similarly, for the cork layer, the resistance R2 is given as L2 divided by K2A. Again, we put the values of L2 and K2 here. We get the R2 value comes out to be 2.326 degrees Celsius per watt. And for cement layer, R3 is given as L3 divided by K3A. So L3 is 0.06. That is 6 centimeter thick as given in the problem, divided by K3. K3 is 0.72. So what we get is 0.083 degrees Celsius per watt. So total thermal resistance is the addition of all three thermal resistances. So that comes out to be if we add everything, what we get is 2.766. Okay, so this total thermal resistance is given by what? Total temperature difference divided by Q. So T1 minus T2 divided by Q, that is given as total thermal resistance, RT, isn't it? So we can rearrange this equation and we can find out Q. So Q comes out to be 16.27 watt. Is it clear to everyone what we have done so far?
Yes, sir.
So this capital Q is heat gain per unit area.
Yes. All right. Now in the second part, what we are interested in finding out? We are interested in finding out the temperature drop across the individual layers, isn't it? So T1 we know, we don't know T dash. So if we consider a brick layer, the resistance of the brick layer we already know, 0.357. That is what we have calculated, isn't it? Correct. So, and the temperature difference will be temperature difference divided by Q will be what? The individual resistance, isn't it? So we can rearrange this equation. What we get is T1 minus T dash is given as Q into L1 by K1A. L1 by K1A we have already calculated, that is 0.357, and Q also we know. So Q is 16.27. So we can calculate the temperature difference T1 minus T dash. That comes out to be 5.8 degrees Celsius. But T1 we already know. T1 is 30 degrees Celsius. So we can rearrange this equation and we can find out the interface temperature between brick and the cork layer. So T dash comes out to be 24.2 degrees Celsius. Similarly, we can find out the interfacial temperature between cork and the cement layer. So T dash minus T double dash will be given by what? Q into the resistance offered by the second layer, isn't it? So L2 by K2A is 2.326 and Q is again 16.27. So from this we get this temperature difference as 37.8 degrees Celsius. But in this equation T dash we have already calculated. T dash is 24.2 degrees Celsius. So we can again back calculate T double dash. So T dash comes out to be, T double dash comes out to be minus 13.6 degrees Celsius. Again, we can calculate the individual resistances offered by each layer. So percentage resistance offered by brick layer is going to be what? This individual value of resistance divided by the total resistance of 2.766. So 0.357 divided by 2.766 into 100. That gives me the percentage resistance for each layer, isn't it? So for a brick layer, the percentage resistance comes out to be 12.9. For cork layer, again, the resistance offered by the cork layer is 2.326 divided by total resistance is 2.766 multiplied by 100 is obtained as 84.1. And for the last layer, the individual resistance is 0.083 divided by total resistance is 2.766. What we get is the percentage resistance offered by the cement layer is 3%. Okay. Now in the last part, what is been asked is if the rate of heat transfer is decreased by 30%. That means the desired rate of heat flow will be what? 70% of the actual rate of heat flow which is present now. So Q multiplied by 0.7 will be the new rate of heat flow. So that comes out to be 11.39 watt, isn't it? So if I wanted to get this much amount of heat flow, what should be the resistance offered? Overall resistance offered that I need to calculate. The temperature driving force is same, isn't it? 30 minus or minus 50, so that is 45. Rate of heat flow, the new rate of heat flow we have calculated as 11.39. So new thermal resistance will be 3.95. Remember this 3.95 is higher than the current thermal resistance, isn't it? So total thermal resistance currently present is 2.766. With that we are getting the rate of heat flow as 16.27. But we wanted to decrease this rate of heat flow further by 30%. So the new thermal resistance comes out to be 3.95. So how much additional thermal resistance is required? 3.95 minus 2.766. And this additional thermal resistance will be provided by what? This additional thermal resistance will be provided by cork layer, isn't it? So this cork layer, how much thickness of this cork layer I need to increase? That is directly, so this additional 1.184 we require to provide through a cork layer. So that means if we multiply this by a thermal conductivity of the cork layer and area, we will get the additional thickness of the cork layer required. So that's why we are multiplying this thermal conductivity of the cork layer, and the area is already 1. So that means additional thickness of the cork layer required will be 5.1 centimeter. So the total thickness of the cork layer will be 10 plus this 5.1 centimeter. That will be the total thickness of the cork layer required if you wanted to reduce the heat flow by 30% than the present value. Is it clear to everyone? Hello?
Yes, sir.
Everybody lost or what? Hello?
Yes, sir.
Yes,
Clear.
sir.
Yes, sir.
Yes, sir. Yes, sir. Understood.
Yes, sir.
Okay, so then we stop here. We will continue from this point in the next class. Okay. All right.
Thank you, sir.
So stay safe.
Thank you, sir.
Thank you,
Things
sir.
are not good outside.
Thank you, sir.
So please take all the precautions, and those who are in the IIT campus, please take care of yourself. Okay, the cases are increasing. All right.
So where will you upload the slides, Moodle or Teams?
It's already recorded in the Teams.